Well, good afternoon. So I guess I'm the last pony in this show for the day. My name is Alan Mantooth. I'm a professor at the University of Arkansas, and I'll have a slide that introduces me a little bit more in just a moment. But actually, before I get started, I wanted to kind of take a quick poll so I can level set myself in terms of the audience and their expertise level. So how many of you consider yourself power systems people? Doing electrical engineering, power systems. What about power electronics particularly, Professor Monty? Okay, well, that helps a lot, because I was a little concerned when I heard the talk from Professor DeDonker's student that it was pretty intense on power electronics. This is not intense on power electronics, but more so on the cybersecurity end of it, and a lot of it relates to energy systems, but I'm going to use an example that relates to a grid-connected device to the grid, okay, and to help you appreciate some of the issues that we're now starting to see in some of these sustainable energy systems. So the topic is cybersecurity, and we're not going to talk about a lot of mathematical algorithms or anything like that. I'm not going to put you to sleep with things like that. I may put you to sleep, but it won't be over that. But it will help, I think, raise your awareness of some of the issues that we're dealing with currently in the field, okay? So let me start with just a brief introduction of myself and my group, and then I'll move on to the content. So I actually run 3 national centers of excellence in America. The first one up here is on the topic of today's talk, cybersecurity. So this is funded by the Department of Energy, U.S. Department of Energy, and the U.S. Department of Homeland Security. And it's a multi-university center. It includes MIT, Carnegie Mellon, Lehigh University, Florida International, and Arkansas Little Rock. It's a different campus. And then the University of Arkansas Fayetteville, which is the lead. Okay, so I direct this center. And as you can see, the title is SEEDS, Secure Evolvable Energy Delivery Systems. So securing oil and gas grids and electric grids, not just electricity, but oil and gas as well, okay? Then I also run a center on grid-connected advanced power electronic systems, or GRAPES. That's 10 years old. SEEDS is about 4 years old. I'm actually past president of the IEEE Power Electronics Society. I just stepped down, so this is that slide's dated, sorry. I forgot to update it. And then I'm deputy director of an engineering research center. Now, to put this in context, the NSF, the National Science Foundation, this is their very largest award to engineering. So this is their most prestigious award. It's a $40 million center over 10 years, and we're not the lead on this. I'm the deputy director. The lead is University of Illinois, and then Stanford, Arkansas, and Howard University in Washington, D.C. So obviously we're very heavily involved in electronics, grid, security, okay, very vertically integrated program. POETS is all about, the name doesn't really tell you what it's about. It's really about electrified transportation. So this is electric vehicles, heavy trucks, heavy equipment, okay, all of that. So mobile systems, stationary systems, and how you secure them. So that's the thing, okay? The UA Power Group, these are the faculty members involved in our group. This is the largest in America. If I gave you a quiz and said, who has the largest power program in America, you would not have named Arkansas. But that's actually the case. So Arkansas is the largest. It's bigger than MIT. It's bigger than Georgia Tech. It's bigger than Virginia Tech. This is the largest program right here. And it's very vertically integrated, as you can see in the things that we do. And some of them are devoted to cybersecurity, among other things, and others are focused more on the hardware side, okay? But this group has grown tremendously in the last 5 years. So half of these professors, 7 of them, are there less than 6 years. So a very young group now, very much changed. And also several of them have already established themselves quite nicely with the NSF Career Award, which is a very nice starting point to their career. So that's our group, very, very large. And of that, there's about 80 graduate students involved in various activities, roughly. And remember, these young professors haven't really gotten their feet under them yet, so as their programs grow, that number will grow to about 140, I would guess, roughly speaking. Okay, roughly 10 per professor is usual for the U.S. system, okay, in terms of PhD students. What I'm going to talk about is I'm going to spend some time giving you a context for all this cybersecurity stuff. You know, why do we care about it, and why do we need to be doing research and development in this area proactively, and how it's different than a lot of research that we do. Cybersecurity vulnerabilities, just to give you some examples and kind of scare you a little bit, give you some examples of different attacks. This is always fun. This is sort of like Halloween stuff, you know, so it's kind of boo. But anyway, so it kind of gives you a little start. Then I'll talk about different elements of security. What's the strategy behind securing a grid or a piece of equipment that goes onto the grid? What's the things we need to pay attention to? There is a strategy, and we design it purposely. Okay. Then talk about cyber architecture, and then finally several slides on testing and evaluation of cyber solutions, and this brings it all the way to home to Aachen, actually, and then I'll just wrap it up. So if you have any questions, feel free to stop me. Okay, I'm gonna try to not go too fast, but I do have several points that I do want to make here, and I don't have 90 slides, so I'm not going to fill 90 minutes with death by PowerPoint. Okay, so if you look at how solar energy has taken off, we've all seen this huge revolution that has taken place globally in terms of the production of solar power. Okay, these are U.S. numbers, and everything I present will be U.S. numbers, but it's the same the world over. We're starting to see it take off, and the cost going down dramatically. Okay, dramatically, more than we even predicted it would go down in terms of the development of solar modules, as well as the power electronics are just practically dirt cheap now, you know, compared to just 5 years ago, and so it is really taking off, and so, but you know, so is wind. Wind is also another renewable that's taking off, and yeah, it goes through its sort of plateaus, but it's generally trending upward and upward and upward. It's happening in the U.S., it's happening in Europe, it's happening all over the world where people really want to demonstrate a diversified portfolio of energy and a balance, okay? In America, I don't think we're ever going to get rid of nuclear. I don't think we're going to get rid of coal, but what we have done is we've taken coal from 45% down to 25% in the last 10 years. And there will be coal, okay, but there will be nuclear, there will be renewables, and there will be a balance throughout that in our case. And that's just the nature of both the politics, the jobs, and everything else that goes with it. It's an economical thing. But it has some advantages, and that is resiliency. When we lose one source, we may not lose another, et cetera. And so that's one thing that is king in the U.S. Mentality is reliability, ultimate reliability, and not doing without, okay? They just don't want to do without. And one of the ways in which they're dealing with that is the growth of storage, okay? So, yes, nuclear will go down. Yes, coal will go down. Like I said, I don't think they'll disappear, but they'll go down. And as renewables increases and takes up more and more of that, the need for storage, as I said, for reliability and availability of energy is going to be handled by storage, okay? And so, again, another huge growth curve. Well, in order to properly operate all of these renewables, don't we need to communicate with them, understand their status and state, whether it's, you know, is the wind really blowing that hard out there? You know, or are we just using wind predictions? No, we have to really know, how is it performing? Same with the solar, same with the state of charge on energy storage. So, and again, it all comes down to, if I understand the state of the system, then I can optimize and predict and refine those algorithms through machine learning and other sorts of approaches, and I can have that reliability, resiliency, availability I'm looking for, okay? So that's the objective. And so I don't think you find in America people, I mean, you hear politicians spouting off, and what they're doing is trying to get, you know, jerk things one way or another just to get a vote or two, but or they have an ulterior motive. But if you factor out the politics, I think the general population, including the power providers, believe in the model of a balanced portfolio, okay, and believe in what it brings for them in terms of revenue and in terms of uptime. Okay, and that's what they care about from a business perspective. They're incentivized to do it and penalized if they don't. So let's take an example. You take this solar installation, actual picture of one in Arkansas. This is a relatively modest-sized solar installation. It's called Ozark 1, and it's kind of interesting. The utility built this and then started selling shares in it. So purchase power agreements for individuals. I can buy into this solar farm, and it decreases the cost of my bill. Okay, and so what I'm looking at here is through these types of purchasing agreements, it will levelize the cost of my power, and I won't have a fluctuating bill. They'll just average it, and that's what I pay, and that's the end of it. Okay, so there's lots of possible solutions like this being presented around the country as examples. Okay, so again, I'm just setting some context here. Same with energy storage. Now you see the huge Tesla bank of batteries here next to a tremendously large solar farm in California. This one may be in Arizona, actually. And again, they have the opportunity with this kind of energy storage to make money through peak shaving and other things. They can make money off of the energy storage. Okay, and when you're locating these kinds of solar farms nearby wind farms, you have a very complementary source. You have daytime, nighttime renewable energies right in one footprint, and energy storage to bridge the gap. It's a wonderful model because the Midwest part of America is where all the wind is, or really good wind. Okay, so you get nice laminar flow. It's the Great Plains, not many trees. You get a nice laminar flow, okay, of wind, but it's also very sunny. Okay, and so you've got the best of both worlds there in the middle part of America, and a great place for energy storage to actually make money. Okay, so again, as you look at this, when you think about most efficient use of generation resources such as peak shaving, and contributing to sustainability, okay, that's where battery energy storage helps you out, and any sort of intermittency can be leveled out very easily. But advanced controls, communication, and coordination are needed for this to work. Oh, that means communication, that means control systems, and that means somebody can hack into them. Okay, and that's why cybersecurity. Okay, because if someone starts, they may do it for a variety of reasons. They may be simply wanting to steal power. Okay, I have a friend of mine who's VP of operations for one of our power companies, and he's in court one time a month from someone trying to steal power. Either the guy died because he was trying to short out something and he didn't know what he was doing and he killed himself, and his family is suing the power company because that guy was too stupid to not use a metal ladder. Okay, just all sorts of strange things. But nonetheless, it can also graduate all the way up to state actors trying to bring the grid down and learn about how it's operated. So there's lots of different possibilities there, and we'll talk about some of those in a moment. So let's transition to the vulnerabilities that we now see. Okay, so I apologize, you're going to hear a lot of jargon you've probably never heard before if you've never dealt much with cybersecurity. They have their own lingo. I had to learn all this myself about 5 years ago. There's a thing called man-in-the-middle attack. I once knew a song, Man in the Middle, but that was a different thing. But anyway, this man-in-the-middle attack, we're sitting over here with a substation on one side and the operations center on the other. So obviously the operations center is communicating with all of its substations. You see this big picture up here that's intentionally blurred. And waveforms and other sorts of things. This is an operations center, okay? They're looking at the grid real time, okay? And they want to know the state of this. If a bad guy gets in the middle of this and starts sniffing the communications, learning about the different protocols, if things are in the open, then they can take a command that goes, let it pass through, see what returns from that command, and then they can begin to spoof, basically, those commands coming back. So they can fool the operator into thinking everything is okay, or into thinking something's wrong and forcing the operator to take action. Okay, as a result of the masking of the information coming back to the operator. So The operator's eyes and ears out into the substation are via some sort of network. Whether it's a private network or not, it doesn't really matter. Okay, some of this stuff is done over power line, some of it is done through cellular networks, some of it is done through internet type of protocols. There is a huge mishmash of methods used in America. There is not one standard. Everybody has their standard, it seems. So there's lots of different. There's standard protocols, but there's just a lot of them that are used, okay, on the order of 15, okay, different protocols that are used, okay. So, technically speaking, this man-in-the-middle attack, it occurs when an external attacker is capable of intercepting, modifying, or suppressing, or replaying network packets, and undetected by tricking the two communication nodes that believe they're still communicating normally, okay. Now, I have a little statistic for you. This is kind of a quiz. So, in the U.S. grid today, how long do you think is, on average, it takes for the U.S. operators to determine that someone has gotten into their system and is listening? Just take a guess. How many days? How many hours?
3 days.
3 days? Okay. Anybody else? 24 hours. Months, okay? 3 months. It takes 120 days before they even know someone is in there. That's terrible. That's awful. 120 days. Our center told them we could figure it out in 1 day, and that's terrible. That's terrible. 1 day is terrible. But it's 120 times better than 120, so that's the math for today. Thank you very much. But so in fact, many times the actors get in and they're simply listening. They're not doing anything. They're just learning. Learning. That's all they're doing. It's hard to detect. 120 days before we detect. And usually it's because they did something. They slipped up and did something. Or some anomaly occurred, and just the fact that they were in the system, it showed up. Okay? So they're just like a ghost. They just come in and they listen. Okay? So another bit of jargon. I've got several of these. So denial of service. Now you probably can guess what denial of service is. Okay? You've probably seen these sorts of attacks on a computer. Okay? And certainly it involves communications, a buffer overrides, these sorts of things. You just flood the processor with a lot of useless calculations and it can't do the things you want it to do. Okay, that's a denial of service. And that's exactly, it's rendering a service unavailable either through a direct or indirect attack. Okay, and I'll give you an example of this in the Ukraine attack in a moment. Okay, it could be physical attacks, just cutting wires, but well, I'm talking about cyber, not physical security. So we're just going to focus on the cyber. But once again, substation operations, you could have people that are attempting to prevent a key command from going from the operations center to the substation by simply jamming the communications, okay? Either by flooding it or whatever. A spoofing attack. Now, what is a spoofing attack? Well, all right, in this case, we're looking at, we're using more and more things like phaser measurement unit type devices where we're monitoring, metering the system, think of the PMU as the device that sits out there, just simply takes measurements on the system, gives us information, and they use GPS timestamping and so forth. Well, what if I were to go in and sort of modify the timestamp just a little bit? Oh, see, I'm starting to make what I think is the real-time state just a little bit old, okay, while I do something, okay? So this is the act of sort of doing a GPS spoofing attack. And again, as we start using more and more advanced gear to coordinate, to process the state of the system, to manage these energy flows that we want to manage, and utilize more intermittent sources like solar and wind, but try to levelize and balance out their intermittency, well, that calls on the new gear and the new communications to be able to do things more in electronic speeds, microseconds, nanoseconds, not, milliseconds and more. So we have that ability to control things rapidly. So we want to make sure the information we've got is good, okay? It's not been spoofed. And if it has been, well, then that's where microseconds can make the difference, okay? That's where just changing that timestamp can make the difference, okay? So, of course, supply chain attack is an old problem. This is something that you've heard about through the semiconductor world, building, counterfeit devices, in some country. We design it in Germany, and we have it manufactured overseas, and we come back and guess what? It's not exactly what I sent over. There's either added stuff or, next thing you know, someone has taken my design and now they're making copies of it, and selling it for 10 cents on the dollar because I did all the design, but they stole my design. Okay? Happens. So that's the old example of supply chain attacking. Well, when you're thinking about building gear for our national grid or the grid here in Europe, this is another one of those problems that you may need to be concerned about, because if they start dropping little extras onto the boards, that's their listening device right there. Okay? They're processing all your signals right there. So we have to have a secure supply chain. We have to understand all the pieces of that puzzle. I'm not going to really talk much more about this, maybe just one more instance of this a little bit later on, because this is really more physical security, quite frankly. The supply chain is the physical hardware, and as it makes its way through. There are cyber solutions to checking it, however. Okay, you've heard of checksums, of course. Well, things analogous to checksumming and that type of algorithm is what's used to determine this processor does exactly what I designed it to do and no more. No less, no more. It does exactly what I designed it to do. And I can test that with software after the fact when I get it back. So it comes down to verification and validation. Okay, I build it, it comes back, I check it. That's the key. So let's go to this example of the Stuxnet, right? You've heard of this one, I'm sure. And this is a case where the malware was introduced and it was targeting industrial systems. And in fact, once the malware was in, then it was able to take over the facility and actually send function calls to field devices and take out almost 1,000 nuclear centrifuges. Okay? So in fact, this is when the world woke up and said, "Ooh, they can get inside my industrial control system. They can go inside ICS and penetrate and do bad things and cause things to blow up." So let me give you an example. You got a 1 megawatt battery sitting out here. What if I took a breaker and just started doing this to it and hitting your battery? You got a fire right out there. That's what's going to happen. That thing's going to catch on fire. Okay? So if I attack it, all I have to do with my mouse button to start a fire. That's all I have to do to start a fire. If I get a hold of it, I can really destroy it in a hurry. Same thing with capacitors. You know the last thing you want to do is start shorting out capacitors. Okay? All right. So that's the kind of thing that this was doing, is getting inside the control system that manages switches, speeds of the centrifuge, other things, and just let them go. Okay? So in the Ukraine attack, a similar thing, and Fiona set me up nicely when she referred to the Ukraine attack this morning. So as she pointed out, there was a spearfish instance. She talked about the USBs. Okay, they got in by directing people to not only the USBs, but that they then were directed to a website which looked very legitimate. They typed in their credentials. Boom, they had them all. As soon as they typed them in, they had their credentials. They got in, installed the malware. Okay. Got access to the industrial control system, or ICS, okay? So the credentials, they accessed their virtual private network. They were actually even able to access workstations remotely so they could see what people were doing to respond to what they were about to do. They listened for a while. That's what's not typically mentioned, is that they were in the system for a while before they did anything. Very designed, coordinated attack, okay? And when they began the attack, of course, the firmware disabled or destroyed devices. Okay, so they took substations offline. Okay, so I think it was on the order of 30 substations were taken offline, and a couple 100,000 customers lost power. And then they introduced a denial of service attack, and they flooded all the call and service centers so none of the customers could get through to tell the operators they were down. So they didn't even know they were down for a while. They were down and didn't even know it because they completely were masked. They were completely coded in. What they were looking at said the system was up, the system was down. Okay? So that kept him offline for more hours than otherwise would have happened. It could have been worse. They limited what they could have done. It could have been much worse. They could have taken that whole grid down for, days and weeks. They didn't, just for hours. What a lot of people don't know is that when this happened, on the anniversary of the next year, they did it again. Now, you don't hear about that much, but they did it again. So they were right back in the same system and did the same thing. And this time they just sort of ping, we're still here. So not so good. And yet it was all done from the comfort of their computers in wherever they were. It was not boots on the ground sitting outside the wall or anything like that, but it was an attack nonetheless on that nation's grid. Okay? Another example is this industrial control system cyber kill chain. Okay, this is another example where this is a common attack scenarios against electric utilities. So listen to this one. First, they get into the system, as I said, 120 days before we even know they're there. And what are they doing? They're planning, they're preparing, they're figuring out how they've made their intrusion, okay, and now they're trying to figure out how they're going to explore and exploit this, and insert their malware, and exactly, how are they going to hide their presence even once they start their attack? How are they going to try to mask where they are and what they're doing? Because they're going to try to deflect it. Okay, they misdirect you, essentially. Okay, stage 2 is they go into their attack development and they're validating that what they want to do is correct, and they launch the attack itself. Okay, and so when they're in the industrial control system, and let's see if I can do this right quick. Yeah. Right here, I think if I control that. So you can kind of look here a little bit. You can see they're in the planning phase, reconnaissance, weaponization, targeting. They're listening for where are the vulnerabilities? Where could I do the most damage? Or if I don't want to do the most damage, where do I leave a crumb behind, knowing that's the worst damage I can do? But I'm going to go over here and cause an outage of 30 substations. And they're going to think, oh my God, what happened to me? The real problem is still sitting in the system. They sent you over here, everybody's appalled, people are getting fired, et cetera, big review, and they're still in your system. Because they planted something and you never looked for it. Okay? So this is targeting. Okay? Then they do their work, and at the end they're trying to figure out how do I what is the next act that I might take? And in our case, we're sitting here trying to figure out, okay, well, how am I going to detect this attack once it's been initiated, and then how am I going to perform forensics on what I didn't prevent before? Okay, so my job is to do the forensic analysis and discover everything that's in there. Okay, as a cyber defender. Okay. All right. So it's a common scenario. That's the kill chain that they follow. Okay. So here's the Halloween part. This is the part that's supposed to give you a little boo. Every 32 minutes, sensitive data is sent outside an organization. This organization is a U.S. utility. Okay. Every 4 minutes, a high-risk application is used. What is a high-risk application? I'm using some application that isn't cyber secure. Okay, it has vulnerabilities. Every 81 seconds, known malware is downloaded into our system. Every minute and a half. Every 53 seconds, some sort of robot is communicating with our SCADA system. Every 30 seconds, a threat emulation event occurs. And every 5 seconds, a host accesses a malicious website. Every 5 seconds. So I don't think the Ukrainians are to be blamed, okay, as not following standard procedures. It just happens that if you're doing business, you're coming across these things. Every 4 seconds, an unknown malware is downloaded. Not a known malware, an unknown malware. So they rose over 900% since this report was done in 2016 over the next year. So they went from 970 per hour to 106. Why? Because people are planting more things out there. They're wanting you to trip into these things. Okay? So I want to bring up a little website here that you might find fun. I assume this computer's connected. There we go. So what you're going to see here is a map of the world. Okay? And these are all the attacks that are happening real time, that are being detected. Of course, if they're not being detected, we don't know it. All right? And so if you look at this, it shows that, and for some reason that's not running. Okay? I'm not sure why that's not running. That's too bad. There we go. Maybe it's because I needed to click in it. I'm not sure. 29 million attacks yesterday. Okay? And 6.6 million today so far. And this is where I'm sorry, that's not real clear, but you can see Texas, USA, an attack on New York. So that was within the country. We have bad actors within the country too. But this will tell you the origination and the target attacks. So if you go to this center, and I can give you this website, but what you'll see is that there'll be attacks and then response to attacks. We'll see all those attacks on Israel, China, India, being launched from California. What you're going to see is many of them will originate in the U.S., and then many of them will target the U.S. You'll see certain ones from China. You'll see them from Russia. You'll see them from Europe. Earlier this morning, I was watching this, and there was a lot of them coming out of the UK. There's some out of the UK, and most of them attacking Germany, actually, weren't going the other way. But so there you go. For something going on in Botswana right now, I don't know what. Okay. But what that is that's servers around the world that someone has access to, and they're making a coordinated attack on something. So the attack may not actually be from those countries. That's just where they have servers sitting that are launching the attack. Okay? So, yeah, it's kind of interesting. And so 29 million in one day, pretty hefty stuff. So now you can see where some of these statistics come from. Okay? So that's the Halloween stuff. So now let's kind of shift gears. The point is, you can see that when, it was so funny, the day that we found out that we had won the award for our cybersecurity center, they called me on the phone and said, y'all have been selected for this center, but we can't issue the award until next month because we were hacked today. How rich is that? I went, boy, you need a cybersecurity center in a bad way. And that was the Department of Energy had been hacked. So they get on the order of 1,000 attacks an hour in the Department of Energy. That's just the funding agency. They don't have anything really all that secure, but they're still attacked ruthlessly. Okay, so it's amazing, and yeah, I mean, I guess people make a business out of this. But so what I want to talk about, back to the topic of grid and grid connected devices, is let's look at current cybersecurity at the field device. So this is something that's deployed in the field. So you're looking here at a solar panel and a solar inverter. This is one of those smart inverters, right? And you've got weather data that you're collecting, time of use data, perhaps if you live in an area where you have time of use pricing, the SCADA system, okay, the communication system, and this is the sort of the user SCADA, so forth. And this might be connected in a neighborhood like residential power, residential solar. Okay, many field devices have little or no security associated with them at all, period. It is so easy to hack them. Give me a sophomore in college and 15 minutes and I'm in. It's that quick, okay? It's really not hard, okay? There are compromised communications, easy to do if there's no cybersecurity, okay? Even if they're encrypting it, sometimes it's pretty easy. Suboptimal performance of the devices, okay? So in terms of being able to generate poor performance if I get in, grid destabilization if it's a coordinated attack, damage of equipment and or residents. As I said, if they happen to have energy storage connected in here, I can start a fire. Okay, I have all the materials I need to start a fire. So before you buy that Tesla wall and hang it on the wall of your garage, you want to make sure it's secure, or at least remove all the flammable stuff from around it. Okay, and then the unintentional load shedding. Of course, this is if someone gets in and they can just start turning off the devices and that sort of thing. So there's a number of things that can be done once they're inside. Okay, and of course, I'm going to use an example that talks about kind of a smart inverter here in just a moment. It's a little bit more than that, and talk about how all these things could happen. So there's 5 approaches basically when we're trying to design cybersecurity. We're trying to design solutions. Okay, one is eliminate the bad guys, and I don't mean with a gun, and I don't mean shocking them if they reach up and touch it either. And I don't mean physically eliminating them, but eliminating them virtually, okay? And that actually, believe it or not, means unplugging or really being very careful to apply the other 4 things such that you have effectively achieved elimination. Let me explain, okay? Protect the perimeter. What do we mean by this? Well, this is typically what you think of as your communications, okay? They have this jargon they call attack surface. Attack surface is meant to be some sort of mathematical representation of how you're vulnerable to attack and what you need to defend against. So you do an analysis of your own hardware to determine how could it be attacked. Is there a USB port? That's one potential way to attack it. Is it connected through communications? That's a second way. Okay. How does one actually log into it? Do you have communications over power lines? That's a third way. Any way into the system, okay? And I'm talking cyber-wise, not unlock it, open the cabinet, and throw a screwdriver in there. That's different. That's a physical attack, okay? So I'm just talking about the cyber, okay? So that attack surface represents the perimeter. That's the perimeter. So, of course, you protect the perimeter. Make sense? Okay, that's one strategy. All right? Another is reducing vulnerabilities. Well, what does it mean to reduce vulnerabilities? Well, this may be the design of your system. If you design your system a certain way, it will be less vulnerable to attack. And you may actually be able to make it such that even if someone were to attack it, you can spoof them into thinking that they've succeeded when in fact you've been watching them all along and you fooled them into thinking that you're not really a solar inverter, you're a hot water heater. Okay? So because remember, it's just an IP address. And I can rotate those. And I can do fancy things. So I can reduce my vulnerability by just making my network a little bit less tangible, a little bit less static and structured. Okay? But I can make it a little more fluid. And it's also easier to detect them. Think about, have you ever looked through a screen? You notice how sometimes it's kind of hard if it's static, but if you kind of move the screen a little bit, you can see through it a little bit better? It's the same kind of notion. I can see you better that you're in my system if I move things around a little bit because you're not moving with me. You're still. That's the whole principle. Okay? I purposely have a little motion in my system and you're not moving with me. And I can change the frequency of my motion. Power electronics. That's the beauty of power electronics. We have a switching system inside, and we can just change that frequency ever so slightly, give up a teeny bit of efficiency just to see if anybody's listening. Because we can do a Fourier transform of some signal, and all of a sudden we know you're there, okay? Because you didn't move with me, and you didn't know when I was going to move. You see, we can use power electronics as, you've probably heard, or some of you may have heard, maybe you haven't, we can take a solar inverter that's on the grid, and we can do a lot of ancillary functions. We can use it as a meter. We can use it as we can use it to detect whether or not a cable is broken by sending a signal out of the inverter on purpose down the line and measuring the reflected wave. Yes, it is a TDR measurement system. Okay, you can use a power electronics device just like that. No added hardware. You just have to program the DSP to do the right thing, and it'll do that. Just send a pulse, and you know, well, if I can do stuff like that, I can use that same processor to do other things. Okay, and I just have to do it ever so often, you know, asynchronously or on some schedule that only I know. Okay, this is how I reduce vulnerabilities. Okay, segmenting the architecture. Let's talk about that. So I had my identity stolen about 1.5 years ago. I guess it's been 2 years. Yeah, I had my identity stolen. Whew, how wonderful was that? Someone filed my taxes for me. And the IRS called me up and said, you know, I think someone's filed your taxes because they don't think you're married. And you've been filing married. Did you get a divorce? I said, no, I didn't get a divorce. And yes, someone has hacked into my system. And what happened was the University of Arkansas, in their infinite wisdom, decided to go to an online system for producing what's called the W-2, which is your earnings statement. The online system, believe it or not, had a 6-digit code to log in. And it was all numeric. Now, characters between 0 and 9? Really? I mean, I could have been in that system in that quick. And so they hacked in and they got my Social Security number, mine and 1,000 other people that work for the university. Okay? And I started filing taxes just to see if they could get some returns. Okay? Because they got my Social Security number. What they didn't do, the dummies that they contracted with, not only did they have a stupid interface, but they didn't segment the architecture. You should never be able to get to the private data from the public interface. Never, never, never. So if you're running a utility and you have customer data, that customer data should never be accessible from the web. Never. That sits somewhere else, segmented. Okay? You cannot get to it. That's important. That's segmenting the architecture. You do the same thing when you build a solar inverter, a smart inverter. You segment the architecture, and I'm going to show you how to segment one. Okay? And then lastly is reacting to a breach. What do you do when something bad happens? And this is actually something you have to design when you're designing power electronics that connect to things like battery energy storage and other things, and bad things can happen. You have to have an alternate control system that understands bad behavior. You've probably heard of a state machine, right? A state machine has all the states of the system, and it'll transition from one state to the next. Okay? So all digital systems have typically state machines, and they go from one state to the next. But a state machine doesn't necessarily elaborate all states, all possible states. You know, there's a thing called don't care. If you're familiar with digital systems, there's the state don't care. And there can be a lot of don't care states. In the cyber world, we care about every state. Because the don't care state is what the attacker wants to get into. He wants to sit in the don't care state that you're not going to pay attention to, okay, and try to send you there at some point, and he's waiting for you. Okay, that's. So you have to design your control systems for your hardware. This is what goes into your DSP, your digital code. You have to design that control system to tidy up every loose end. Okay, and you always assume the attacker wins. What do you do about it? You have to go to a fail-safe. If they win, you have to shut down to a mode that is basically iron and steel. The grid. You have to go back to iron and copper and steel. Okay? And just let the grid operate in what we call the dumb mode. Okay? And all this smart grid stuff, okay, somebody hacked it, but we still have power. Okay? And we just have to lock them out, and we have to let things just work. Which means we disable the solar, perhaps, or we disable the batteries until we get there to repair and recover. But we don't allow bad things to happen. Fail safe. That's reacting to the breach. Okay? And you think that's easy to do? That's not always easy to do given some of the power electronic devices we're trying to put in the grid. Sometimes a fail safe mode, it's not so straightforward. It's not so straightforward. So I'll give you an example. There's a company in America making a thing called the Grid Energy Router. It's a device that mounts on the power pole right next to the service transformer for the residents, okay? And this device does volt-var support. So basically, it adjusts the voltage, okay, and injects a little bit of power here and there to produce a power factor of 1, okay, for the customer. So, but it saves the utility a lot of money, okay? So it's great for the utility, it's great for the customer, okay? In that case, that device has a nice dumb mode. It just says, oh, somebody hacked me? I'll just quit operating. You just don't get my help. And everything's fine. So they have an excellent, it's just a bypass mode. Boom, close the switch, copper. They don't do anything else anymore. Okay, everything's good. In other cases where we've got things like fault current limiters that are protective devices, what do? Just not limit the current? And if you don't limit the current, the breaker that it's coordinated with is destroyed. So the option isn't to just quit playing in that case. You got to do something, okay? You got to do something. And designing that in, that's real engineering time. That's real creativity and thought. So designing in cybersecurity features like that, it's not $0. I'll talk about that a little bit later on, okay? So those were the 5 approaches, okay? The elements of security involve, okay, confidentiality, and in this case, we're not necessarily talking about privacy. It is more encompassing than just privacy of personal data, okay? It includes the confidentiality of communications and other things that you're trying to do. The availability, okay, so availability of data, okay, well, I have them elaborated here. And then integrity of the data, validity, consistency, predictability, okay? Well, when we think of energy systems, obviously the availability of power and the integrity of that power is very important. Our systems rely on that. They rely on having a certain quality of the sinusoidal AC waveform and not a lot of harmonic content. Our equipment depends on it, okay? It has to conform. And then it just being up, okay? So these are obviously two very big things here, okay? Confidentiality hasn't played as big a role in the power systems until we started having more grid-connected stuff and more smart systems, okay? And smart meters was the first instance of where this kind of started coming up big time, okay? So I'm going to give you an example now. And we're going to walk through an example called a Cybersecure Power Router. This is a power router for the home. This is an invention at the University of Arkansas. We have a patent pending on this. And we've developed it in collaboration with the University of South Carolina, where Professor Monty used to be a professor before he stepped over the pond. And in working with one of his colleagues, we developed this device that I'll just explain what it does because there's no slides that explain this. It's like the solar inverter. You plug your panels into it, but you also put your batteries into it. You put your backup generator into it. You put your grid feed into it, okay? And it connects to the internet. And so what it does is it takes weather data and time of use pricing, and it predicts your solar availability, maintains a certain state of charge on your batteries, and basically reduces your bill by using as little grid power as possible. Because it puts power onto the mains right into your home. And so that power is available. You don't have to pull from the grid. It will backfeed the grid if you're allowed to do it. It contains an automatic transfer switch between the grid and the backup generation. So the two are never on at the same time. So if the grid is up, the generator is off. If the grid goes down, then it commissions the generator to turn on, and all of these power electronics synchronize to the signal coming out of the generator. If you don't have a generator, then this power electronics has grid forming mode, and it will generate a 60 hertz or 50 hertz sine wave. It'll generate the right frequency and do its own frequency regulation based on its power. So if you have a power outage, you can completely island, go off the grid, and this thing will manage your energy resources, okay? So this is something that we've developed, and we did it for less than $1,000, okay? Now we're securing it cyber-wise. and that price is going to go up because, and I'm going to show you how we're cyber hardening it, okay? Because the first version, just hardware prototype, okay? So roughly a 5 kilowatt level device, okay? Well, this is the way any power electronics device, not just ours, is architected. This is your circuit, your power electronics. So it's a hardware layer, and there's controls to control the switches in here. You saw those PWM signals that Mr. Swee was talking about earlier, okay, where he was talking about controlling those power electronics. That's resident in a DSP or a microcontroller or something controlling this power electronics. So it's software, okay? There's a control layer, okay, and then there's a supervisory layer. Now this is the primary, this is the secondary layer, okay? Now this supervisory layer is looking at not just one power converter, but the fact that I have multiple power converters inside this box. One for solar, one for batteries, one for generator. I have lots of different interfaces, okay? And so I have to manage that as well, okay? Then there's a tertiary layer, okay? Whereas I'm taking all the commands and communications, and I'm doing also energy management. This is where the energy management resides, okay? So I've got energy management algorithms at play here as well. So all of these are areas, and this is just, think of it as layers on an onion, okay? And inside is the power electronics. At the fundamental level, there's hardware, okay? Power modules and capacitors and stuff like that, okay? But then you've got all this software layered around it. This is called segmenting my architecture from a software perspective, is making sure I do indeed have these, okay? And in order to communicate between them, internal authentication. That's hardware hardening number one, or software hardening number one. When I communicate between layers, there's an authentication, okay? It has to be fast, really fast, okay? Because when I send a command, I want it done now, okay? Zero latency. So, but still, we have encryption at that level. So that's the first level I can tell you about right now, is between these layers, everything is encrypted. And of course, this is the attack surface up here. This is where people can come in from the outside. You can't get right into here. There is no USB port on this thing. There's no way to get right into this stuff. You go through here to get down to these, okay? It's set up that way on purpose. There is no side door, no back door. Okay? You set it up that way on purpose. Okay? All right? So that's the first thing. So this is a simplified diagram, okay? This is that attack surface. You've got the utility communication, you've got utility power. Okay? So this is connecting to the mains, and you can communicate over this, by the way, and people can put a clamp on it, and they can listen to what's coming over the power, so they can kind of decipher some of the things going on. My job, hardening this to make sure that the information they get is just useless, okay? And actually, I can use my power electronic switching and my harmonic generation on purpose to completely mask what I'm doing, okay? So they won't get anything useful. They'll get what I give them, and I actually give them something to chew on, okay? So this is me spoofing them. It's the stuff they listen to over my power line is total trash, okay? Because I know the spectrum of signals, and I bury my good stuff inside it. They don't have my encryption key. They don't know how to take that away to get my signal, okay? Spread spectrum stuff. You're familiar with this. This is radar kind of stuff, okay? Just using it for power electronics. All right, the utility communication is the standard communication stuff. This is network communication. This is like the 5G stuff that would apply here that Fiona was talking about. All the things that will get developed for that, we're happy to adopt. That's perfect. Other people will solve that problem, not power electronics folks, but people who do network security. The network security people will harden this, and we will adopt and utilize communication security protocols. And I think she mentioned this morning, no one's really hacked the 4G LTE stuff, right? Okay, well, then that would seem to be pretty good. Why would we be inventing stuff like that? But that's already in place. But we have to assume that they get in. As I said, you always assume that they breach the perimeter so that you can put in some sort of defense mechanisms by design inside here. And so all of these things you see in here, you notice now there's two DSPs. Why is there two DSPs? Because I have a power router in the loop. I can tell you what's going to happen when I do a patch before I do the patch. I receive the patch, I bring it in, and I put it on DSP2, and I simulate with it. And I have a model predictive algorithm sitting right there on DSP2 before I flash it over to DSP1 and start using it. Or I simply switch DSPs. I don't really flash it over. I just switch DSPs. And I just do a seamless handoff. So I build in redundancy. So it doesn't matter if you hack my patch. When I try to patch my system, any connected device like your phone has to be patched. Upgrades, whatever. Well, these will be no different. Smart inverters will be no different. So when they accept a patch is when they're most vulnerable, because we're letting in the communications. So it's something embedded in the patch. I can tell you right now, before I ever go real time with it, whether or not it is. Furthermore, this allows me, if I have let's say 300,000 of these devices in the field, what's my sequence of bringing them online? Do they all take the patch and come online at once? Or is there some sort of progression, coordinated progression? I can put that coordination right there. So they all know when they're going to go off. Timestamps, okay? So I can have it automatic, and I can also have it as an override. So I can coordinate patching. And when you're patching millions of devices, like smart meters, you want to do something like this, okay? All right? So, again, this is the same thing. Fail-safe hardware controls. Remember I said fail-safe? What is the fail-safe for a device like this when it has energy storage connected to it? Well, one thing is neglect the energy storage. Okay? So one of the things I have to fall back to is that I kill that port. Okay? And whatever I do, that port goes off. I have a fuse or something I blow or something, and that port goes off. So I do not burn down someone's house. Okay? So if somebody gets in and I don't like it, I pop that fuse. Okay? And there is no connection to a battery. They can't sit there and bounce around with my battery. Okay? So there's things here that we can put in place that are cyber controlled that allow us to control the hardware in that way. These are the kinds of things I'm talking about, cyber hard by design. Okay? Let's keep going. So here's an example of this Cybersecure power router in terms of the controller. This is the universal controller board that we designed. Basically has all the I/O and the two processors. And it kind of gives you some of the rundown here, where it has the secure communications within it, key management and encryption, layered security, firmware integrity checks, hardware protections, segmented architecture, flexible control methods. Okay? In other words, I have control methods that keep me going when things aren't so good. Okay? So fail-safe doesn't always mean shut down. Fail-safe may just mean step back. Okay? Check again. Step back again. You may have several generations of retreat before you have to just say, give up. They've really compromised me. Okay? So, again, it's sort of thinking like the old castles and series of moats and bridges or walls and so forth. You kind of think like that in terms of stepping back, and then what can you finally defend? Okay? All right? So let's take an example of our power router with the man-in-the-middle attack. So we've got our device connected to the home. Maybe we've got 10,000 of them connected to homes. Okay? So there's a bunch of these guys out there. And we got a control center. And we have normal communications with this. Again, it could be cellular, it could be over the internet, a lot of different ways to communicate with it. Encryption and key management strengthens the confidentiality of the communication. We talked about confidentiality being one of those three main things. And we need to have confidential communications. Okay? We can't be giving away our commands or letting people listen and take our commands. Okay? And also the state space modeling and hardware protections that I've talked about, they prevent a message from damaging hardware or causing malicious power flow. Malicious power flow is just dumping all the current into the batteries, even though they're fully charged, just continuing to heat them up. You know, maybe not such a good thing. Okay? So we don't want to do anything malicious. Knowing this keeps us from knowing that that could happen, it keeps us from allowing that state to occur, okay? So this is how we're going to deal with someone who's trying to intercept our communications, okay? We assume they eventually win, and what do we do about it? So there's sort of two layers here, okay? In the denial of service, of course, again, it's communications, right? So the operator sends a command, but it maybe never makes it to my device, or I never get a proper acknowledgement back. So I think, somebody's done something, when in fact, maybe they haven't done anything. All he's been able to do is intercept my command from being acknowledged, but he doesn't really know what to do other than that. I don't want to do something as the operator that would then cause a problem, because nothing's really wrong, okay? So this is what we mean by segmenting, the management of the power, from the controls that manage communication. So we've segmented those in the two layers that we talked about. We don't let those things reside together such that you can't go from one to the other. Once you're in one, you can't go to the other without a whole new round of hacking and working at it, okay? The spoofing attack, as I said, we're using information that's coming, wirelessly to us, weather data, other things that we're collecting. So if they were to send us false weather data saying, it's not going to be sunny today, so your solar panels are going to be no good, yet I've got a perfectly sunny day, could I mismanage the energy? At worst, I would just mismanage the situation, run my bill up, right? Because I take all my power from the grid thinking there's no solar. Now, of course, we're going to have instrumentation that would, bear that out, but still you get my point. In a simple analogy, that could be an issue. So hardware-assisted monitoring will detect anomalies in a wide range of things. And we've got some of this hardware-assisted monitoring built right into the system where it's monitoring things and it's sort of helping us do checks and balances. And because it's hardware, it's fast. So this helps us from the latency issue, okay? So let's see. So the supply chain attack, this is sort of back to firmware, and this is what happened in the Ukraine attack. They didn't think they could get into their firmware, but they actually got right into the firmware. Okay, that's why they were able to leave breadcrumbs behind. They got into their firmware. Okay, and before that, people just felt like you couldn't do that. You'd never get into their firmware. They did. And so, in fact, what we are doing with this architecture is checking for the integrity. And this integrity check quickly reveals the difference between an official patch and a corrupted one, for example, okay? And as I said, Casper can act as a processor in the loop, okay, to test firmware in the real world with real data without risking damaging the actual hardware. Why? Because it's actually running in parallel, okay? So I spent $25 on another DSP. Go ahead.
I know that the firmware is written on a ROM memo. It cannot be rewritten. Mm-hmm. How do they get in the firmware?
Yeah. So you got to read and write. You got to read from that memory, right? So that's where they get it. Is they're intercepting your communications from that read-only memory. They didn't change the firmware, but they actually manipulated it. They manipulated it in a way that they got into your system to a degree that they manipulated what was actually written there. One of the things that we feel like they could do is they could flash a new firmware in the ROM, because that's what a patch often does, is it's updating your firmware. And so in point of fact, that's actually what they can do, is they can actually flash a new ROM and, it came through authentication checks. It should be good, but you had no way of validating it in a behavioral way. You just validated it with, pardon the simplicity, with checksums and stuff. You validated it that way. Oh yeah, the packets look right. They had the right key. Sure, it's valid. Load it up. Oops. And that's what this architecture I showed you avoids, because we'll sit there and run it, and we'll run it through some scenarios. And when we're convinced it's okay, then we'll start using it. Okay. So highly unlikely if we have advanced detection methods, things that would detect in a more sophisticated way, the penetration of someone, highly unlikely that a bad patch is going to make it through. Okay, and this gets back to the sophistication of what you put into this. And for someone who does hardware in the loop, Professor Monty can tell you, I mean, your simulations are only as good as your models, right? And so this is only going to be as good as the model predictions and the behavior that we model in the processor in the loop system. But at least we're actually in the system when we're doing it. So it's real-time work. Okay? So the final layer here, cyber hard by design. That's the term that we use. Okay? So it requires, robust protection requires multiple layers. Layer your architecture. The hardware level, submodule authentication. Yes, we're even doing it at that level. Custom keys, encrypted communication between the submodules. External authentication, of course. Okay, software and hardware intrusion detection. Some of this is hardware assisted. Okay, so some of this is dedicated hardware on the board that's there only for the purpose of detection, real-time detection. Okay, it's not the DSP. It's different hardware that's often introduced to help us detect. Okay, new encryption techniques, of course, is an area of research that would be. Control systems must address all possible states, not just the ones that allow the thing to function. And then, nonsensical destructive acts must be disallowed by design. Okay, that's the difference. Okay, and you'll find that even gear that is on our system right now, made by the biggest vendors that you could imagine, we have hacked them all. Okay, but we don't tell you that and we don't publish it. We call them, talk to them, tell them what we found, and they do the right things. That's the interesting thing about this area of research. You can't publish everything you learn because why would I do that? That's not in our all best interest, is it, right? It's better to contact the vendor and say, we found a vulnerability, let's have a chat, and then they go off and do their thing. And sometime a patch occurs. And no one ever knows where it came from. And that's fine. Okay? The world is a better place. Okay? And that's the way that a lot of this kind of works. Okay? But, so you don't publish everything. But the other thing is, unlike the design work that we do when we design hardware, design power electronics to do a function, and our biggest enemy is time and temperature. Time and temperature. It's the environment. And time. It ages. We have a real adversary here. That's someone who's trying to debunk our design. They're trying to defeat our design. And so that means I have job security, I guess, because I'm always going to be trying to be more clever than the people trying to get into it. So a real adversary makes for a different situation. So there are certainly costs. I've alluded to them already, and I didn't want to leave it on the table that there aren't costs to this security. Okay? Processing of overhead, you can't throw a sledgehammer at this in terms of encryption. You're going to impact the operations too much. Okay, certain operations within the grid depend on a certain timing. They depend on an acknowledgement signal within a certain time frame. You can't go outside those bounds. Okay. So that means that sometimes additional resources are required, and that increases costs, and it may lower performance a little bit, but that may be the necessary evil. That's why we care about the advances of things like 5G and other things. That increased bandwidth gives us more time to do what we need to do because the communications will be so much faster. That's good. More headroom I get, better off we are. Okay. The impact on system operation and stability, of course, this is the time delay of communication. I already touched on that. And the additional development time of grid-connected power electronics. We all want a smarter grid. You don't have a smart grid without power electronics. I'm sorry, it's just not going to happen. Communications is wonderful, but communications does not steer power. Power electronics steers power. Okay? It's the muscle behind the smart grid. The power electronics is. It's the muscle. Okay? The nervous system may be the communications. Okay? And the bones are all those wires. Okay? It's the hardware. Okay? I like to use the human body model. But the muscles are the power electronics. That's what's going to make it move. Okay? So, and in order to do that, you got to design this stuff in. And these design points I was making, that's what needs to happen. So this is what ABB and Siemens and Allen Bradley and Honeywell and different people, this is what they're focused on. This is what they're focused on, putting into play, okay? So I'm going to mention now, so the last part of this is test and evaluation, and I'll wrap up. How am I doing? I got 15 minutes? Yeah, okay. Should work out fine. Oh, he's got an animation in here. I might have to keep going back. We have a very large test bed at the University of Arkansas. This is a 6-megawatt test facility that is set up for a cybersecurity test bed in addition to being a power electronics test facility. So think of the test facility right next door. That's 5-megawatt capability, okay? And think of the big wind turbine that you have down the street, okay? Now put all that together into a test bed and make it available for people to hack. Oops, maybe not, okay? But this is part of what we've done here. And so it's a large-scale cybersecurity test bed. And yes, as I said, there's a lot of communication protocols. Here's some of the ones. And, you know, industry standard hardware devices. So you have real-time automation controllers, protection relays, PLCs, security gateways, various network devices. And these things are all connected, you know, in a system that allows us to reconfigure it, sometimes hardware, sometimes software-wise, okay? And to do different attacks in different scenarios, okay? But basically to test our own algorithms too. So when you think of the hardware systems, you know, the classical systems, I mean, this is a one-line diagram, and that thing definitely wants to keep going. There are, you know, it's 480 volt all the way up to 13.8 kV. It's 15 kV class, grid simulator, regenerative load banks. It's basically a microgrid in and of itself, okay, with different systems I can put on and off the system. So there's lots of smart inverters in here, for example, different things like that, that I can act as one going bad or something like that. I can emulate a lot of different scenarios, okay? And then there's all the software systems. Some of these are commercial systems like checkpoints, then other network simulators and routers and switches and so forth, simulation resources, okay, and hardware in the loop capability, okay. All of this is put together in a huge emulation, evaluation, simulation environment to determine, well, that thing is really going nuts over here. I think my student, when he put these slides together, gave me a little bit of auto forward. But the point is still this, that there's a lot of possible scenarios we can look through, looking at real power flows. Golly. Yeah, I'm being hacked. Golly. I can't keep this thing still. I think I'm going to use this, I'm going to put that down. No, it definitely has got a timer on it. Real power flows, okay, and now I'm going too far. Golly, let's check this. In addition to hardware in the loop capability, you've got the real power flow work, so you actually are steering power around to actual loads in some cases. Yeah, I know this thing is probably going to go all the way to the end, just let it go. And you've got and then you've got simulated or emulated assets. So in a situation where I might have let's say a distribution feed into a neighborhood, and I've got some community energy storage, I've got some residential solar, gosh, going all the way to my conclusions. I've got, just don't pay attention to that man behind the screen there. I've got this whole scenario painted out. I can run that emulation of that situation, some of it in real hardware, some of it in hardware in the loop, so it'd be virtual or simulated, and some of it actually running, you know, the MATLAB type of activity, or OpenDSS or something like that. And I can scale this architecture to, you know, many buses, okay, through something like OpenDSS coupled with the real system, So maybe I'm looking at only hardware on one bus. I can put all this together in a single evaluation and look at a lot of different scenarios. Now, why do I do this? Just simply because I want to try to, what will happen is when we're starting to do evaluations of cybersecurity, a utility will come in and say, we want a situation like this. And it's my job to try to emulate that situation as close as possible. So that's what I'm trying to convey here, is that it's configurable in that way. It's not that I'm going to sit here and run through all these different millions of scenarios, because there's more scenarios than I could probably do in my lifetime for a lot of these. So what you do is you come up with a sort of situation that a utility is interested in, then they go after it. They evaluate it. They may even try attacking. They may do things in this playground, okay? And then once they're finished, then they're ready to say, okay, I'm convinced I want to try to run a field demonstration. And what you did is you just emulated the situation I'm going to put it in, okay? And that's the whole point, is it's a step above alpha testing. All of us might write a piece of code and run a little test on it, right, to see if it's doing what we expect. That's alpha testing. This is kind of the beta testing before it goes to a demonstration by utility, and then, at that point they're ready to say, okay, this is sort of past all of our sanity checks. It's ready for going to a commercialization, or we may use it internally. So, and really, I think that there's really no other, in terms of the summary, there's really no other conclusions there. So I'll just jump to here. As we start increasing the number of devices on the system, we're obviously increasing the attack surface of the whole grid, if you look at it as a grid system, or even a portion of the grid, okay? And grid edge devices, they're not exempt from this malicious attack. We think of substations and operating stations as being the main points of attack for people. It's not necessarily true. There'll be far more grid edge devices out there than there will be substations. And you can imagine that the utilities will do a very good job of ratcheting down on those substations and control centers, okay? So, as they start improving their cybersecurity. So that just means that we need more advanced detection and mitigation techniques in the power industry. And detection, I already mentioned, is a big problem, okay? So there's a lot of research going on into how to better detect that an intruder's even gotten in, okay? Then the mitigations, what do we do then? They're there, what do we do? How do we flush them out of the system? How do we distract them? And that's actually one of the more effective things that we found works is things called honeypots, where you set up something and you sort of draw the flies to the honey, and they fall for it. And once you've got them, you've got them, and now you know how to flush them, okay? So if you can draw them toward, this is what I meant by trying to make your system look a little bit less static than it looks today, is they're not quite sure what's real and what's not. And we actually ran a test like this, where we did, with those 2 megawatt generators that I have, we made one of them virtual. Looks just like a real one, okay? But one of them wasn't real. And we were able to draw a group of students trying to hack straight to it, and got them. So we do try to have a little hackathons from time to time. You want to have some fun. Turn a bunch of computer scientists loose on your system. Whew, that's nerve-wracking. So the cyber hard by design, but it's amazing what they can do. Cyber hard by design techniques that I talked about, this is an approach to this threat mitigation. This is where we feel like the hardware companies that are building the smart grid equipment need to be aware of this. And at the end of the day, the customer, and I mean the customer in this case is the utility, they have to be willing to pay the incremental cost. I had an opportunity to interview a man who worked for Westinghouse 20 years ago, when Westinghouse was still making a lot of grid equipment. And he said, we had a whole line of equipment that was cyber secure. Utilities would not pay the extra cost for it. We couldn't sell it. So we gave it up. Well, 20 years ago, we weren't hearing about Ukraine and stuff like this, were we? And you saw how the number of attacks is increasing year over year. I just gave you a quick sample of 100 to 900 in 1 year, how the number of actors is going up. And I think I read an article recently where it's clear that over the last 4 to 5 years, the bigger concern for a lot of people in security positions, whether it's military or whatever it might be, is cyber, the cyberspace. And that that's an increased awareness there. So, you know, I think we're getting to a point where that value proposition might be there for paying the extra engineering costs associated with a gear that's been hardened cyber-wise. So, and I think one of the things that we have to be careful of as researchers in this area is that people have thought about this problem for a while, and there may have already been some really great solutions posed, and they just never made it to market. And so when we write our publications, we have to be careful to say published literature, because companies have done a lot of things on this front already, okay, and are still doing them. They just won't talk about it. So as I said, there's some associated centers here, and this just shows some of those, and this work is really funded and focused out of Seed Center. So with that, I think I'll just, and there's a few references in the back for you as it relates to Stuxnet and some of those other things that I mentioned. Maybe the Ukraine thing is listed there. So you'll have some things to look up later if you want to. And with that, I'll stop and take any questions. I hope I left a little time, not much. Sorry.